Good afternoon, everyone, or good morning, or good evening, depending on wherever you guys are. This is Demystifying Maths. This is my first ever video. I'm going to be doing the video on the Lagrangian today. Just to be clear, the only reason I'm doing this video in the first place is because it's a physics concept, and I do feel that physics concepts deserve more of an explanation than regular maths concepts. I understand that certain maths concepts are very hard to understand, but I still prefer a more elaborate explanation for physics concepts. That's just how I am. I'm sorry, but if I am asked to do a maths concept, I would likely just prefer to do the latex posts that I do usually. Okay, now continuing on. You can see I've already written quite a few things, okay? So the first thing I'm going to introduce to you guys is Q, which is our generalized coordinates vector. Now each element of the vector Q represents a generalized coordinate. So Qj, as I've written, would be the jth generalized coordinate. Now what is a generalized coordinate? I've written that too, sort of, but I'll just explain it. One, very obviously, a coordinate that describes a dynamic system. Any dynamic system that you can define a coordinate for. All the coordinates basically you can possibly define for any dynamic system would be a generalized coordinate. There are a few other rules as well. Now these set of coordinates must be independent and must completely describe the system. What does completely describing a system mean? That you should be able to figure out the position of each distinct body or element involved within the system through these set of coordinates. They must be independent, so I'll just explain that bit. And the third bit is that they should form a holonomic system. A holonomic system is formed when all these coordinates are independent, as I said, and you can define constraints on such a system in a way that, in this kind of a way, such as that a function of time and your generalized coordinates should equal to 0. Again, you can have as many constraints as you want on such a system. I won't be going too much into detail into holonomic constraints and constraints in general, because I will give you guys I will give you guys a general overview of what it is, but I will not be explaining it in detail. Nonetheless, a holonomic system is formed when all the coordinates are independent, and when there is a function that you can, or multiple functions can be used that are in terms of time and the generalized coordinates, such that that function equals 0 or any constant, though 0 is preferred. Now, for generalized coordinates don't have to be specific to the Cartesian coordinate system or the spherical coordinate system. I should probably just add that. Or the cylindrical coordinate system. They can literally be anything you want, as long as they can describe the system and are independent, and in total form a holonomic system that can have constraints applied to it, holonomic constraints applied to it. You can use it for the Lagrangian. Okay, now I'll just explain that. What does independent exactly mean? So there is something called a degree of freedom within any system. Degree of freedom basically refers to an axis of motion. This axis may be rotational or, well, positional, depending on what you want, but both are allowable. So for a general double pendulum system, you may have, or you guys may not be familiar with a double pendulum system, but I'm sure you're familiar with one pendulum at least. So for a single pendulum, you usually use the angle between an imaginary normal line and your actual pendulum and define that as theta 1, correct? Now for a double pendulum, usually we're used to the system that is theta 1 and theta 2. So just another angle that is between the normal line on the secondary pendulum's point of connection. I don't exactly know what to call this, but you can see it. The angle between this imaginary normal line and the point and the second pendulum itself. Okay. So now in total we have theta 1 and theta 2. That gives us 2 coordinates and 2 degrees of freedom. And you can obviously guess, since this is a pendulum of fixed length, both pendulums would have a circular path, which is like this and like this. Sure? So moving on. Now I will describe the same system with a different set of coordinates. Here you can see I've defined this as a point of origin, and I've defined the position of the first mass on the pendulum as x1 and y1, and the second mass as x2 and y2. Okay? Now y will obviously be the horizontal distance from this point of origin. Let's mark it in red. Okay? Now x1 and y1 would be the two coordinates that define the position of the first mass on the pendulum, and the second pendulum's the mass on the second pendulum its position would be described by x2 and y2. This gives a total of 4 coordinates because x1, y1, x2, y2, 4. Now you know that from the previous system, as I showed, both pendulums should have a circular path, right? So this has to go like this, and this one also has to go like this. Now the difference between an independent set of coordinates and a dependent set of coordinates is that when you bar or fix one of the coordinates, you should still be able to have some degree of motion within the other coordinate. What that tends to mean is that basically, suppose since this system has 4 coordinates, if I were to fix something like x1, so x1 goes away. Now I should still be able to have motion within y1, x2, and y2. Some motion. I'm not saying the full axis of motion, but some motion within these axes. So obviously you can still move the second pendulum, x2 and y2. This will still completely move, but x2 is fixed, and as you remember, this pendulum is of fixed length and has to have a circular path only. So I can't really move this pendulum up and down because x1 has to be fixed, and the only other degree of motion left should be y1. But since this is a pendulum fixed length, I can't really move this system up and down. So I can't use this kind of a system to describe this. I can't use this set of coordinates to describe this double pendulum, at least if I want to use the Lagrangian for them. So this will not work with the Lagrangian. This one form a holonomic system, so I can't use it. Now, going back to the top, we have a little quantity called S with our generalized coordinates vector in square brackets, and we've described it as the integral of T2 of the Lagrangian, which is a function of time, our generalized coordinates, and q dot. Q dot refers to the derivative of our generalized coordinates in terms of time. I would like you guys to remember that because I will use the dot notation a lot in this post because I just prefer it. So I hope that's fine. Nonetheless, this is actually the definition of our quantity S. What is S, you may ask? S refers to the action. The action in a very basic sense is a linear function. First of all, let me just describe what s is in the first place. It's a linear functional, which is why we have the square brackets around the q. Now, what is a linear functional, you may ask? A linear functional is any kind of quantity or transformation that takes, or basically any linear map that takes inputs in Rn, n preferably being more than 1. Actually, it has to be more than 1 for it to be a linear functional, and transforms them into, or maps them to a single number on our field. Your field can be anything. Your field of scalars could be anything that you want. I've just chosen the real numbers because, well, it's classical mechanics. I will use the real numbers. I don't see much use in using complex numbers. You could probably use them when you've reached quantum mechanics, or in general just Hamiltonian dynamics. But that is way far ahead of this kind of, I would say, lesson or explanation, because I'm just trying to teach you the Lagrangian for classical mechanics. So, S refers to the action. We're calling this the action, by the way. Now, the action for any trajectory of a particle would be the sum of all the little actions that take place. So, actually, I should change this to D capital S, just to make sure there's no confusion between small s, which would be the arc length. So, ds, this would be a differential element of our quantity s, capital S, not small s, which is r. So this would be a little differential of action. The little differential of action is the Lagrangian times a differential in time. Now this is the definition. Again, I can't really change it. I can't really explain it in much of a sense, except that this quantity is defined in this sense because of the principle of least action, which is basically Hamilton's principle. Hamilton's principle is that delta S by delta T should equal to 0. Delta refers to the variation, by the way. And just to be clear, delta is an operator in such a sense that if I were to use something like delta P dot, let's say, I can bring the delta inside and the derivative outside. So I can say that is d dt delta P. I can do that kind of a thing with such an operator. Delta basically refers to a variation within some quantity. Okay, so delta S by delta T has to be 0. This is Hamilton's principle. If I were to write it down more accurately, Hamilton's principle is actually from a given time t1 to t2, the variation in total kinetic energy minus the variation in total potential energy plus the variation in the external work done should be 0. That's the entirety of Hamilton's principle, or in general, the principle of stationary or least action. Now, this principle also kind of assumes one thing, which is that the variation in the position at t1 should be equal to the variation in the position at t2, both of which have to be 0. This is an assumption made by the principle, and I can explain why this principle is considered true, but to mathematically prove that this system is equivalent to Newtonian mechanics, I don't think I will be doing that. I'll provide you guys with an example showing that it's true, but I will not be proving it completely. Now, the explanation behind this is that any particle, also if it isn't clear, I'll just write it. The Lagrangian is T minus V plus WE. WE refers to the external work done, V refers to the potential energy, T refers to kinetic energy. Also, a lot of systems just don't acknowledge WE because external work done has to directly affect this body. And that should be, this external work has to be, this external work could be something like resistance. But something like, so anything else that you may refer to with external work is not useful. So you may add this WE term only suppose when there's a fixed path that you need to follow, or suppose when your object or body is, or system of bodies is experiencing friction or resistance in those cases. But otherwise you can omit this term and just use L equals T minus V. I apologize for my handwriting, it's a bit odd looking. Also, if you're wondering why I use the weird kind of L, it's just to remember that it's the Lagrangian, I'm just used to it. It's nothing special. You can use the regular L if you want. Most people use the regular L, I use this weird L. It's the same thing. Now, T refers to the total kinetic energy of the system. I'll just write it. V refers to the total potential energy. And this is just the external work done. Okay, now let me just explain why this Hamiltonian's principle comes into place. So Hamiltonian's principle believes that, states that for any dynamic system within classical mechanics, that is, the value of the action has to be minimized. So by minimizing the action, you're saying basically that the potential energy has to be maximized and the kinetic energy has to be minimized, and so has to be the work done minimized. But external work done can depend on several factors, so I won't go much into detail because of that. I'm sorry, one second. I'm a bit ill at the moment, if that's not a problem. I'm sorry. Okay. So, T minus V plus WE. Hopefully that's fine. The reason Hamiltonian's principle says that, I'm not exactly sure, but in a simple way, I could say that most particles tend to want to stay still. They don't like moving a lot. So by minimizing the action, you're saying that you're minimizing the total kinetic energy and maximizing the total potential energy. And as I said, particles in our universe tend not to like moving a lot. So the opposite of movement would obviously be harboring potential energy. And by maximizing potential energy and minimizing total kinetic energy, the behavior that particles tend to prefer is observed in a sense. I guess that is one explanation of it, but again, this principle is limited to classical mechanics and is also limited to the Lagrangian Hamiltonian formalism. That's all. Now, continuing on. So, I hope we've understood that this is the Hamilton's principle. Delta S by delta T equals 0. And now we're going on to the Euler Lagrange equation. And I'll be showing you how we can do that. So delta S over delta T is equal to 0. Delta T is obviously arbitrary, so we can multiply it out and say basically delta S should equal to 0. Now S we described as this quantity. So we'll further go and now we'll talk about delta S. Also, I apologize if my deltas look a bit weird. I am not the best person at writing, to be completely honest. So, I hope that's not a problem. But anyways, continuing on. So, if you don't remember, I took the delta inside the derivative earlier, and I'm going to do that again. I'm going to take it inside the integral itself. So we get t1, t2, delta L dt. Now, we know from general calculus, or just not general calculus, just calculus, that partial L by partial, sorry, not partial, dl by dt should equal to partial L by partial t plus partial L by partial q. I should probably assign this like a summation. That might help actually. dl by dt should equal to partial L by partial t plus the sum of all, sum from I equals 1 to n being the number of generalized coordinates we have. So partial L this is just a general identity or rule for the total derivative of any multivariable function with respect to one input. Partial L by partial t plus the summation from I to n of partial L by partial qi times partial qi by partial t plus partial L by partial q dot I times partial q dot I over partial t. Now, let me just remind you guys that this term is actually just partial q dot I. Actually, no, it's just q dot I, actually. Yeah, and this term is just q double dot I. Though I'm not going to write it as that, if that's fine. Because as you can see, this is dl by dt. Again, the delta operator and the dl by dt aren't exactly the same thing, but they are different in some way. And if you remember, I said that the Lagrangian that we are defining for now is going to be time independent. So this term is 0 in a sense. So we get dl by dt is this sum. Now I'm just going to multiply this by dt out. I know it's not a regular fraction, but just follow me here. Also, if it's not clear, qi and q dot I are both just functions of time, technically, because they are the position with respect to time. They may be independent, but we'll just treat them. They may be independent, but we'll still treat them as regular single variable functions at best. So you can actually write this partial qi by partial t as dqi by dt. Same goes for this one. Instead of partial q dot I, you can just write partial or dqi dot dt. Okay, now since we've multiplied by dt, we can get rid of the dt at the bottom, so we get dqi so we get this. Now all I'm going to do is change these two d's to deltas, because they are technically variations, just not with the limit applied. So we get delta s to equal to the integral from t2 to t1 of the summation from n to I equals 1. From I equals 1 to n. I am so sorry for the noise in the background. I hope it's not a problem. I'll just change this. So changing the d differential elements to delta operators or variations, we get this. Now, after getting this, first of all, what we have to do is, you can see that, also this is the delta operator, if it's not clear. You can see this is technically similar to the product rule. So we'll just apply integration by parts to it. So just remember that dq dot I, or delta q dot I, is the same as d delta qi over dt. Okay, so the I will put delta q dot I here, and we'll put partial L by partial q dot I here. Again, all this all the derivatives and integration right now that I'm doing have to be in terms of time, because that's the differential element for our integral. So the derivative of this would just obviously be d by dt partial L by partial q dot I. And this just be the delta qi, because we can see this is the derivative with respect to time of delta qi, so we get delta qi here. If I were to write this out, we multiply these two terms and write this as the new integral. So we get partial L by partial q dot I times delta qi at t2 and t1 plus the summation, I should probably write the integral first, plus the integral from t2 to t1 of the summation from I equals 1 to n of partial L by partial qi minus the derivative with respect to time of partial L by partial q dot I times delta qi dt. Now, if you may remember, the first assumption, one of the few assumptions you made, that the variation in q at t1 and t2 have to be 0. And this term has been multiplied by the variation in qi, well, so we'll just assume that the variation in qi, so by 0, I basically meant the 0 vector, actually. So the 0 vector is just a bunch of zeros, so delta qi at t2 and t1 both have to be 0. So this should just be the integral from t2 to t1 of the summation from I equals 1 to n of delta qi times partial L by partial qi minus d by dt partial L by partial q dot I dt, which has to equal to 0 as per Hamilton's principle. So now I can actually bring the summation outside, giving it's still going to be the same answer, by the way, if you're worried. So now partial qi is always arbitrary, and it's a variation, so it always has to be positive. So the only way this term, this integral itself, can be negative is if all these subsequent terms were 0. And you could argue that these could have differing terms, but you should remember these all are independent. So there is no way that for all dynamic systems these terms would sum up to 0. So since these coordinates are independent and the variation in qi has to be arbitrary, not always 0, so we get that partial L by partial qi minus d by dt of partial L by partial Q dot I has to equal 0. This is the final Euler Lagrange equation that we use to figure out all equations of motion for any dynamic system. Well, that uses the Lagrangian. Again, I am defining the Lagrangian again as t minus v only. Yes, you can use the other one, which is the full Lagrangian, which is t minus v plus we. Alright, I'm sorry for that, but nonetheless, so we have a final Lagrangian, which is t minus u plus we being external work done. I will just explain it. I think this should be enough actually. So I'll just also add the time-dependent Lagrangian, which I know of, is e to the alpha t minus v. I haven't seen a we ever here before, but it could be there. I'm not sure, but it's probably either outside this or something. I am not sure. But this is the most popular one I've seen for the time-dependent Lagrangian. I don't know any other ones, unfortunately. Alright, so moving on, and the alpha, I don't really know how to figure it out. I just seen it a lot. Another thing that you can do is, since I mentioned holonomic constraints were any constraints on the given system that you can define in the sense that a function in terms of t and the generalized coordinates should equal 0. How you apply it to the Lagrangian is that you just add this constant. You add lambda f t comma q to the regular Lagrangian, which is t minus v, or even t minus v plus we is fine. So that's the full Lagrangian with holonomic and generalized constraints. And this is the time-dependent Lagrangian. I haven't really used this a lot, so I don't know much about it. I've just given to you guys in case you're curious. You're free to look up more about it. I could even be wrong about the alpha there, but this is the most popular one I've seen. So this is all I know. And of course, the general, you can have as many. I'll write it out better. 1 second. You can have as many constraints as you want. So it's really actually this. Hopefully that helps. This is the final time-independent Lagrangian, by the way. Usually when I come across constraints, they don't even use like, this is just a general way you should put it, the lambda, that the function should be in terms of time and the generalized coordinates. Though for any time-independent Lagrangian that I've seen, this t is not really needed. It's just a function of the generalized coordinates. But if we're using the time-dependent one, I think you can apply it there. I'm not exactly sure, again, because I haven't used it. Continuing on, I will be showing you one last thing, which is the Beltrami identity, and then I'll be doing a very simple example for you guys that you can compare with Newtonian mechanics, and I'll show you that it gives the same exact result. Okay, so continuing on, the Beltrami identity. Suppose we have a linear function, as mentioned before, of some similar form. Okay, this time I'm going to call it p. Okay, and our function, and p is going to be an integral from a to b of some random function c, that is a function of x, y of x, and y prime of x, and all integrated in terms of x. Now suppose you have to minimize p. For minimizing p, what you would do is, as we used before, since this is exactly, mathematically speaking, it's the same exact type of quantity as s, just this is a random quantity, we're just trying to minimize it. This isn't required in any mechanics thing, it's just an identity I want to teach you guys. Now to minimize p, obviously remember delta p over delta y minus d by dx, or not delta, sorry, partial p by partial y minus d by dx of partial p by partial y prime should equal to 0. That's our Euler Lagrange equation as we found before. Now c has to be, again, independent of x. So if we know that c is independent of x, minimizing p becomes easier, which gives us the Beltrami identity. So as we used this before, if you remember this thing, I'll just use it again, but for c this time. I think I used the wrong letter. It should be partial c minus partial c over partial y minus d by dx of partial c by partial y prime should equal to 0. So now, if you remember from the previous page, or from just a few minutes ago actually, that partial c by the total derivative of c in terms of x should be partial c by partial x plus partial c by partial y times dy by dx plus partial c by partial y prime times dy prime by dx. Oh. And if I were to write this in a better way, partial c by partial x plus partial c by partial y times y prime plus partial c by partial y prime times y double prime. Also, prime represents a derivative in terms of x here. I just didn't use the dot because we're not using time here for our derivatives. Now this term, as I said, c has to be independent of x. That is only when you can use the Beltrami identity. Okay, so this term is 0 again. So we get dc by dx should equal to partial c by partial y times y prime plus partial c by partial y prime times y double prime. Now we're going to isolate this term basically. So we get y prime partial c by partial y should equal to dc by dx minus partial c partial y prime y double prime. Now we can substitute this into our Euler Lagrange equation right here. Where is it? Yes, but first we'll multiply it by y prime. So we get y prime partial c by partial y minus y prime d by dx partial c by partial y prime should equal to 0. Now we substitute what we found here for y prime times partial c by partial y back over here. So we get dc by dx minus partial c by partial y prime times y double prime minus y prime d by dx partial c by partial y prime should equal to 0. Now if you can see, this bit resembles the product rule, which is uv prime, which is uv whole prime should equal to uv prime plus vu prime, and vu is obviously here partial c by partial y prime, which means this is our u prime, this term d by dx partial c by partial y prime, and v would be our y prime, giving this y double prime to be our v prime. Now we can write this entire thing as dc by dx minus d by dx y prime times partial c by partial y prime equals 0. Now since derivatives tend to be linear, we can combine these two, giving d by dx c minus y prime partial c by partial y prime equals 0. Finally giving c minus y prime partial c by partial y prime should equal to some constant a. This is the Beltrami identity, which can be used to minimize any kind of a property or any kind of a quantity, actually not property, sorry, any quantity that is of the form the integral from any constants a to b of some function that is a function of x, y, and y prime integrated in terms of x, such that partial c by partial x is 0. This can minimize p. Now this is a variational principle. If you're interested in why this Euler Lagrange equation is called the Euler Lagrange equation, it's because Euler founded the calculus of variations as a result of Lagrange, a 19 or 21-year-old at the time, figuring out this new formalism to classical mechanics. This was all done during the time when the tautochrone problem and the brachistochrone problem were going around. And you can actually use the Beltrami identity to prove the brachistochrone problem and prove that the shape it takes should be a cycloid. If you don't know what the brachistochrone problem is, it is the problem which tries to figure out the shortest time it takes for a particle to go from one point to another. I mean, the path that a particle should take in presence of gravity to cover as little time as possible. So basically minimizing t. There what you do is you try to minimize t by expressing it as an integral of potential energy. Yes. I think that is the case, which gives you the equation y is equal to something x or t. I'm not completely sure, but that's how you do it. I can do it for you guys later on in a post if that's needed. But for now, I'll be doing a very simple example, which is, I guess, of a pulley or something. Yeah, pulley seems fine. Actually, no, not this kind of pulley. I'll just do a regular pulley. I am kind of running out of time, so we'll let this be M1. We'll let this be M2. We'll let the distance here be y. The position of this can be y1, and the position of this m2 can be y2. Though we do know that y2 has to be, and if I think we can, let's just specify the length of this to be L, which basically gives us that L should equal to y1 plus y2. So y2 equals L minus y1. So y2 dot should just be negative y1 dot, and y2 double dot should just be negative y2 double dot. Okay, so we don't have to use the, I don't want you guys to be using the constraint so quickly, so I've just done it really quickly for you guys. You can use holonomic constraints to do this one as well, though it's not really necessary because this is kind of obvious. If we define the length of the entire rope to be L, you don't need to do it. So since we only have y1 left, first let's define our t. Also, there is no resistance being felt by both these particles, just to be clear. So t is going to be half m1 y1 and dot squared plus half m2 y2 dot squared. Now y2 is just negative y1 dot, y2 dot is just negative y1 dot, so, and it's squared, so the sign doesn't matter, so it's just half m1 y dot squared plus half m2 y1 dot squared. Now we have v, which should be negative mg y, because this y points downwards, not upwards. So negative mg y1, negative m1 g y1, and we need y2. y2 is just L minus y1, so we get minus, because y2 also is downwards if you don't see it, negative m2 g L minus y2. So that leaves us with negative m2 gl minus negative m1 g y1. It should be a y1. And plus m2g y1. Okay, that should be fine, I think. m2 minus m1 gy1 gy1. Okay, so we get our Lagrangian to be t minus v, which is y1 dot squared times half m1 plus half m2 plus m2gl minus g y1. I'm just going to take the negative inside, if that's fine. m1 minus m2. Okay, now we'll use the Euler Lagrange equation, which is partial L by partial y1 minus derivative in terms of time of partial L by partial y dot y1 dot equals 0. So partial L by partial y1 should be g m1 minus m2, g m1 minus m2 minus d by dt of partial L by partial y dot 1. Y dot 1 is right here, it's squared, so we're treating them as independent variables, though they may not really be independent. We just do treat them as that, for the Lagrangian at least. For this formalism, you have to do that, kind of, unfortunately. So you get m1 plus m2, because times 2, I hope you guys remember that, and y1 double dot because the derivative of this, the partial derivative in terms of y1 dot, would be m1 plus m2 times y1 dot, and since m1 and m2 are constants, the derivative of that in terms of time should be y1 double dot times m1 plus m2, and this should equal 0, giving you y1 dot double dot as m1 minus m2 g over m1 plus m2. That you can just figure that out by shifting this to this side, or just adding m1 plus m2 y1 double dot, and then dividing this right side, or well, left side, by m1 plus m2. Both sides, basically. So you should finally get this, and since this is a regular plea, you guys can try it out. I trust you enough to do this on your own. You will get the same exact equation if you used Newtonian mechanics. So that is going to be the end of the Lagrangian from my side. I hope you guys enjoyed it. I will try my best to do more videos if possible. I wish you guys all the best, and I hope you enjoyed this. Thank you for watching.